go back to these MOSFETs briefly, and then I'll go on to nuclear weapons, something that you ought to know, have some idea how they work, what are the issues there. The Mosfe T transistor conceptually is like two p-n junctions. It's got this particular one has p-type semiconductor in the middle, sandwiched between n-type semiconductors on the ends. You can make the reverse. There are all kinds of variations on these ideas, but this is the basic idea and probably the most common of the types of transistors in this category. So when you touch n-type to p-type to n-type, you get this strange situation where the central region, the whole p-type material, and even into the n-type parts beyond the junctions, they have no empty levels in the valence band, and they have no filled levels in the conduction band. So basically, this cannot conduct electricity. You apply electric field in either direction, and nothing much happens. You okay with that idea? It looks like it's a hopeless situation that will never conduct electric current, except that it has this, in principle, a metal surface here. In practice, it's related to metals, but it's a conducting surface up here separated by an insulator. And that's where the MOS, metal oxide semiconductor, is this idea that you got a metal, an oxide, a semiconductor, and it's a field effect transistor. And the field they're talking about is an electric field. So it's a device that uses the electric field of whatever you put on this gate to control the flow of current through the structure. In this case, right now, no current can flow through the structure regardless of what we do. But if we put positive charge for this particular MOSFET, it essentially turns on. It's like an electrically controlled switch. And you can turn it on by putting positive charge on the gate. What the positive charge does is it attracts electrons. They love it, right? So you can actually drag electrons in from the surroundings. In fact, in from both ends and elsewhere. They will come in here to be near the positive charge. And when that happens, those electrons have to go somewhere. They have to have their own quantum standing waves. And since the valence band is already filled with all the levels there filled, if new electrons come into this central region, the only place they can go is into the quantum standing waves associated with the conduction band. So now you've got electrons in the conduction band attracted there by the gate. In concept, what you have done is you've taken the material that was chemically made as p-type material, and you have electrically turned it into n-type material by dragging extra electrons into it. So the characteristic of n-type semiconductor is it has electrons in the conduction band. You can make that happen here by dragging them in with an electric field. So you've sort of turned this central region into n-type material. And now it's all n-type material. Chemically n-type material, electrically n-type material, chemically n-type material. It's one big chunk of n-type material, and it conducts electricity. Is that okay? So here you sort of switched it on. Now it went from being an electrical insulator to an electric conductor. And you can do everything in between. You can make it a medium good conductor, a terrible conductor, anything you like, depending on exactly how much charge you put here. And to show you this, so this is what I was trying to do last time, and I failed. I'll put it up on the side. Ready? Okay. You are now looking down. There's the MOSFET sitting here, and this is my electrical connection to the gate, to that surface that we can put charge on. And the way I've got it set up right now is it is conducting current right now. How do you know? This meter over here, milliamp meter, it's saying it's carrying a whole lot of current, actually, more than I really want to send through it for any great length of time. So evidently it already has positive charge sitting on the gate, turning it on. I can turn it off by taking the positive charge off. How do I do that? Give it a destination that it would love to go to, like the negative terminal. So I'm going to touch the negative side, the low voltage, and I'm going to let the charge leave. So the charge left the gate, went into the negative side, and the MOSFET turned off. I can turn it on by putting positive charge on it. Boop. And I'm putting it on with my fingers. I'm not a very good conductor of electricity, but I'm good enough. I'm putting so little charge on that I can do it with my fingers. Is that okay? And That's the basic idea. This guy with a tiny bit of charge, you can turn that on and off. You can turn on and off actually quite a large current. When it's on, that's enough current and the electric power available here, we could light a light bulb up with it. We could turn off the light bulb, turn on the light bulb. So this stuff is all over the place. I'll stop doing this and I'll go back to, put the camera back up. So bottom line is these types of transistors are everywhere. Transistors was originally transfer resistor. I don't know, does that mean anything? They were adjustable transistors. The early transistors were fairly non-ideal. This is a really almost nearly ideal component. With almost no charge at all, you can turn on and off massive amounts of current. What else about them? They are used when you turn on and off your cell phone, what are you doing? You're putting charge on or taking it off the gate of some power capable MOSFET. When you are doing calculations in your cell phone, when it's trying to think of something or build the image for a browser, it's doing this entirely with MOSFETs. The memory is MOSFETs. You can see this actually already, as I just showed you, it remembers what last I did. Did I put charge on it or did I take charge off? It's a memory. It only remembers one symbol, one binary bit. But this is the basic concept that's going on in all the memory in your cell phone. Any other questions about MOSFETs? All right, so with that, then I'm going to stop talking about audio players. It's just more details about using those MOSFETs to do interesting things, both to create sound, for example, or to store information or to manipulate information. Let me go on to a different topic. And the different topic is nuclear weapons, which they've been part of life on and off for 70 years. So I will ask this opening question here, is it possible to have 100 tons of plutonium and not have it explode? How many think yes? How many think no? Okay, a few people going for no, but the majority going for yes. And actually the fact is the world has well over 100 tons of plutonium around. Is that true? That probably is true. And yet it hasn't exploded. So evidently the answer has to be yes, because just by example. There's something about having a lot of plutonium around that isn't the whole story. The reason I bring this up is because you've heard probably the concept of a critical mass, that you have enough mass of a material like plutonium to get some sort of effect, like an explosion. That's a misnomer. It's not literally the mass that matters. Critical mass would be measured in 100 tons. 100 metric tons is 100,000 kilograms. It's not just having the mass that matters. It's how you structure it. And so we have to look at the whole story of what's called a critical mass, even if that's not quite the right name. About nuclear weapons, obviously, they release an incredible amount of stored energy. So there's a packed full of potential energy that comes out as other kinds of energy. They produce incredible temperatures, radioactive fallout. What's that? We'll do that if I have a chance. And they're fortunately relatively difficult to make, not difficult enough, alas. And they use what's called chain reactions. So the questions we'll go after is sort of where's the energy to start with and how do you release it? Okay, so the story begins with the nucleus of the atom, and I've mentioned it many times, but we've never stared at it in any detail. The nucleus of any atom contains at least protons and possibly neutrons. These are the subatomic particles that are associated with the nucleus. They're called nucleons because, of course, they live inside nuclei. And the proton has a positive charge, one fundamental positive charge, the exact opposite of what an electron's got. And the neutron doesn't have any charge. It's in there. It seems to play no obvious role in terms of holding the atom together, but it turns out to be an important addition to the nucleus. These nucleons, so I'm lumping together, proton, neutron, together they live in the category nucleons. They contain most of the mass of the atom. So if you look at pick any random atom, tin, I don't know, and you measure the mass of all the electrons together, and you measure the mass of the nucleus, you find the nucleus has about a factor of 2,000 times as much mass as the electrons, is give or take. So most of the mass of everything you ever encounter is located in the nuclei of the atom, in that tiny nugget at the center. It is truly tiny. The nucleus occupies about 1 part in 10 to the 15 of the atomic volume. So the atom's this big, and you go looking for the nucleus. If you imagine blowing it up, and here the electron out there, and you go looking for the nucleus. Where is it? It's a tiny, tiny spot there that's about 100,000th the diameter of the overall atom. It's tiny. Consequently, it's almost nothing. It's almost no volume. Because it's got the vast majority of the atom's mass, it also has a vast majority of the atom's potential energy. And where did that come from? Well, this is a consequence of relativity, of the revised theory that Einstein came up with in 1905, observing that the simple laws of motion, as I've described them here in this class, aren't quite right. They're an approximation of a more accurate theory that entangles time and space in an interesting way, and ultimately discovers that objects have energy, that mass and energy are in some ways interchangeable. So if you've got something with a lot of mass, it has the equivalent of a lot of energy, and it is possible in certain circumstances to convert what appears to be mass into what appears to be energy, or vice versa. As the E equals mc squared. That's a famous equation. It's taken out of context, doesn't mean very much. But if you put it in context and churn on it for a while, you discover that there really is an energy associated. E is the energy associated with mass being the mass. So how does this all work then? So if you look at the nucleus and you let's pick one, and for some reason I picked sodium. And part of the background of picking sodium is because these are often called atomic bombs and stuff like that. It's really a misnomer. It's not the whole atom that's involved. It's just the nucleus that's involved. And so a real atomic bomb would be a chemical reaction involving the whole atom or its outsides, in which case if you mix sodium and chlorine and allow them to react, they will react violently to make salt, and they will release energy in the process. And that is the energy that's stored as chemical potential energy in the electrons. And it will release a lot of energy, or so it will seem, and you'll get a nice big explosion. If you you can start fires by mixing sodium with something like chlorine. But there's way more energy available in playing around with the nuclei of atoms rather than the electrons of the atoms. So the proper name for these weapons would be nuclear weapons, not atomic weapons. All the action is in the nuclei. So having ranted about sodium and chlorine being a real atomic bomb, being capable of making a real atomic bomb, which wouldn't be very exciting. Let's look at sodium. The nucleus of a sodium atom has 11 protons in it. And 11 protons are all positively charged. They hate being that near each other. So why do they stay? Well, it turns out that although they repel each other electrostatically, once they touch, they experience a new force that I don't believe I've ever mentioned in class. And it's technically, it's called the nuclear force, and it's attractive. The nucleons stick like Velcro to each other. It's short-range force, like Velcro is. Velcro, two pieces of Velcro, plus and minus of Velcro, they don't care about each other when they're far apart. It isn't until you actually touch them that you get some sticking going on. So the force in Velcro is short-ranged. This would be long-range. Electrostatic force is are long range. They'll reach across empty space as far as you like. They'll get weaker, but they go on forever. The nuclear force does not. It tapers off quickly when you lose contact. And it's attractive. So when you bring 11 protons together, which takes a lot of work, they hate being this near each other. You shove them. They're really close. They make the atom look gigantic. That's how close they are. And so when they finally touch, this attractive force shows up, and it's stronger than the repulsion. So they actually stick and hold. Okay? So I pulled this attractive nuclear force out of a hat, and there it is. And it has, if you wonder, the nuclear force is actually a feature of a more fundamental force called the strong force. There's also a weak force. These are two other forces in nature that I would do if I had more time in the semester, but I won't bother. So the nuclear force isn't the fundamental force so much as it's a feature. It's an effect of the strong force. But anyway, okay, so they stick and touch and stick. And if you were to let go, they would still fly apart. Dang, their repulsion's too strong. So what are you going to do? Throw in some extra nucleons, some extra objects that experience the sticking force, of the sticking nuclear force, but don't experience the repulsive electrostatic force. That's where the neutrons come in. So it turns out a sodium nucleus has 11 protons, and that makes it sodium, because it attracts 11 electrons, and that forms the chemical, the atom that we call sodium. The electrons out there give it its chemistry. The 11 protons are there. But you need 12 other neutrons to show up to dilute the repulsion between the protons. So the neutron's role in nuclei is to let the protons spread out a bit and not be quite so packed. So see the protons and the neutrons together, you get 23 nucleons, 11 of which are positively charged and the others are neutral. That's a stable object. It'll stick together, stay together forever, for the rest of eternity, if you don't mess with it. Okay? That's a sodium nucleus. And if you think about assembling it from just separate objects, separate particles, you bring them in. The neutrons don't care. They're perfectly happy to come to join the party without any work. But you have to shove the protons together. So there's work involved in assembling this nucleus initially, and then when they start sticking, there's actually work done in pulling them in together and binding them up. So it's assembling that nucleus involves storing a lot of electrostatic potential energy in the system, and then releasing a lot of nuclear potential energy in the last touching process. Is that okay? So if you snipped a very massive atom in half, it would release energy stored in it. What energy would be released is as the two parts come apart. You okay with the question? I give you two choices. It's either electrostatic potential energy or it's nuclear potential energy. How many think it's A, it's the electrostatic repulsion between the protons that releases all that energy? How many think that it's B, it's the nuclear attraction between the nucleons? Well, let's try cracking the thing apart. So we've assembled it, and now we split it in half. And the act of splitting it in half does involve investing some energy in it to break the Velcro. And now you've got two halves that are exquisitely close to each other, but separated enough that they're not sticking. And that's where the story starts. You've already done the snipping. And now these two parts push each other apart ferociously because they're both positively charged. One of them's got maybe 6 protons, the other's got 5. They push apart like crazy and do work on you. As you try to slow them down, they drag you apart. The energy is actually electrostatic repulsion. So breaking large atoms releases energy that was stored as electrostatic potential energy. Some old news, we've done that for months. You're allowing positive charges to separate, and the voltage goes down. Okay? So that's where that actually is where the energy in nuclear, in the simplest of the nuclear weapons, the World War II nuclear weapons, that's where the energy is stored. It's actually electrostatic potential energy in protons that were packed more tightly than they would like. Okay, so any questions about that idea? If you snip large nuclei apart, they will fly apart ferociously. The question is, can you snip them? And what's involved in that? So why are some atomic nuclei unstable? Well, you can see that there's a balance between the repulsion of the protons, they hate being near each other, and the nuclear stickiness, the nuclear force stickiness. If you lose the stick for any instant, if certain parts of the nuclei come temporarily unglued from the other parts, and the electrostatic potential energy is allowed to be released, the whole thing will fly apart. Disaster. It'll shatter. The nucleus will fall apart. Why would that ever happen, though? If they've managed to come together and stick, why don't they just sit there and stuck forever? I will tell you that it's possible to try to assemble nuclei that will not stay together. If you try to bring together too many protons with not enough neutrons to dilute them, it'll come apart. So you can't make a sodium nucleus with only 11 protons. You've got to dilute it with neutrons, and actually about the right number. You have to pick about the right number. It turns out if you put too many neutrons into an atom to over-dilute the protons, the neutrons effectively get lonely. They're sort of on their own by them. And neutrons, it turns out, are unstable by themselves. They eventually turn into other particles. They fall apart. So they're intrinsically unstable, and I won't talk about that. I get lost in it for a minute. So you got to have about the right balance between these things, or they'll never stick. You push them together, they come right back apart. But if you bring the right grouping of protons and neutrons together, they'll stick, and they'll seemingly stay stuck. Except if that sort of nuclear Velcro has even a moment of failure, they'll fly apart. And classically, they would stay stuck forever. What's classically mean? Forget quantum mechanics is what it means. In the world of quantum mechanics, these particles are wave-like when you sort of leave them to themselves. And wave-like things don't have well-defined locations. They're not exactly where, at one point in space. And so they explore, have the opportunity essentially to explore more space than they would classically. So the nucleons are sort of sitting there like a collection of eggs in a basket, but not quite. They're fuzzy. And they can occasionally, by random chance, find themselves beyond the stick of the nuclear force. And at which point, they suddenly discover they're basically out of the basket. And if they're repelled by the electrostatically, off they go. They're lost, and boom, they fly out forever. That process where what would be a classical object is in a place where it can't go. It's stuck in place. And my example here is a marble, say, stuck in a dent at the top of a mountain. So you've got a big mountain. It's three-dimensional. This is a two-dimensional view of it. But imagine you've got a volcano. The marble sitting in the caldera of the volcano. And of course, left to itself, classically, it would sit there forever. To get out, somebody's got to give it extra energy to lift it up to the rim of the caldera and let it roll downhill. And classically, that'll never happen unless somebody actually goes in there and does it. But quantum mechanically, for little teeny objects, for example, a tiny marble, basically a nucleon, for example, it's not well located inside that caldera. It's actually a wave, and the wave can be located, it's spread out, basically. It's not entirely in the caldera. It's actually distributed across the top area of the volcano. And it's got the possibility of actually finding itself outside the caldera of the volcano without anybody actually having added energy to it. The wave is weak inside the walls of the caldera because that's energetically unfavorable for it to be in there. It shouldn't be in there. So if you find it, it's not literally inside the well. It would be found up here. If you found it there, it would have to have more energy than you thought it had to climb out gravitationally. But it has the possibility of getting through this what's called a potential barrier, of coming up with, of going beyond a place where it's not allowed to be, classically, and ending up in another place where it is allowed to be classically. Classically, it has the energy to be out here, but it doesn't have the way to get there. So, I mean, this guy could be out here on the edges without violating any energy no energy problems. But it can't get there because it needs energy to make the trip up, over the lip, and down. And quantum mechanically, it can go from inside to outside without truly going over the bump, without ever having that energy that it would need.
What's the difference between classical and quantum?
The difference between classical and quantum, in the classical world, which is the world that we observe mostly for large objects, a bowling ball sitting in a bump at the top of a hill. If you put it in a pothole at the top of O Hill, it's going to stay in the pothole until somebody comes and bothers it, because it needs energy to lift itself out of the pothole and then begin to roll down. If that whole story were shrunk down to tiny size, so that quantum mechanical effects became important, the little tiny bowling ball, say an electron, for example, talking about it as a marble or a ball is not so accurate anymore. You have to describe it as a wave. And that wave has presence in the pothole, now this tiny quantum pothole, but it also has a spread to it. The waves aren't tightly located. They're fuzzy. They have widths and stuff. And they can find themselves outside the pothole. And so the electron can just get outside the pothole. And that's a process known as quantum tunneling. And you hear stories about this, like if I ran against the wall enough times, I would actually I could find myself outside. And, it makes a nice story. I'm truly too big for that to happen. The probability of that is impossibly small. But little stuff does actually go through places that it's not allowed to be. And an example of this is all your flash memory. The flash memory is based on MOSFETs, and there's that gate surface. It has no wires connecting it. It's sitting all by itself in insulator. So how can you ever put charge on it or off of it? You do it by quantum tunneling. They tunnel the charge in. They allow it to go through the barrier, and they let it tunnel off. And once they let it tunnel in, it sits in there for years, because it could leave, but it might take the age of the universe to leave. They have to assist it and sort of coax it out of there and coax it to tunnel through. But that's, it's a tunneling memory. Is that okay? So the point of this is that radioactive nuclei, which you've heard tell about forever, they are nuclei that if they could rearrange in some way, they would be able to release potential energy, typically electrostatic potential energy. And they can't do that classically. So they would sit there forever if the world were a classical world. But it is a quantum mechanical world. We approximate the world when we talk about it in this classical, non-quantum mechanical way of billiard balls. Yeah, Jesse? What is the hill? Yeah, I kind of messed up. The hill is a spot where if the particle were located there, it would have more energy than it actually owns. So imagine you have an electron sitting, a table. I will build a table right here, and I will put some electrons, some camped out negative charge there, and a ring of negative charge around the electron. So the electron's sitting in the middle. It doesn't want to be on that ring anywhere, because that ring's got negative charge. So it hates being there. So that if you were to find it there, it would have more energy than it does right now. So it's trapped in the middle. And it's not but it's not a billiard ball. It's got some width to it. It's a wave. It is a ripple. And the ripple doesn't just end abruptly. It tapers off. And it tapers off as it goes in the vicinity of this negative charge. But it's not quite zero. It's very small. And that wave continues and get outside the ring of charge where it doesn't want to be. So this is a potential barrier. I've illustrated it as though we're a ring of electric charge, but you could hide the ring of negative charge under the table, and it would just look like a smooth table with a ring where the electrons shouldn't be. If you do go looking for the electron, you will most likely find it in the middle of the ring, in the center, where it's happy, where it classically would be found. But if you go looking really carefully, you can find it. There's a small chance you'll actually find it in the ring area where it shouldn't be. And then you might think, well, if you find it there, if it's there, it has more energy than it had when it was in the middle. Where'd the energy come from? It came from your measurement. If you find it in there, the act of locating it in there actually supplies the energy. I mean, who's going to look? Well, you got to look. If you look, you got to sort of like poke at it. The poking adds energy, and if you find it there, you paid for it. You bought it. You broke it. You bought it. Okay. So nobody goes looking for the nucleons as they're sitting there all happy in their waves, and they're all working together. You don't go looking for them to be in the barrier, in the bad spot. You could. If you do that, then you'll end up potentially paying the energy cost of finding them in a place they're classically forbidden to be. But they can go from inside the barrier to outside the barrier for free. Nobody has to pay for that because they have enough energy to be outside the barrier. They just can't get there. And so they tunnel. They tunnel through the barrier. They don't actually go on the barrier because they don't live on. Without effort, you won't find them there. They just drill through quantum mechanics, but the wave goes through anyway. Is that okay? I mean, it's bizarre, but it happens. And this is responsible for radioactivity. So large nuclei. This is nuclei like, well, for example, uranium. Uranium is a really big nucleus. It's got 92 protons and about 143 or 146, as I recall. Yes, neutrons. A lot of neutrons to dilute those nasty repulsive protons. Nonetheless, it falls apart by way of tunneling over long periods of time. What's the problem with large nuclei? Well, if they've got too many protons, there's too much electrostatic repulsion. They want to come apart into pieces and release electrostatic potential energy. If they have too many neutrons, they want to come apart because the neutrons themselves fall apart. And they break into parts. Actually, the parts they break into are interesting to some extent. A neutron can fall apart, oddly enough, into a proton and an electron. And one other particle that happens to be an antineutrino, which is like, what the hell is that? So let's leave that aside. But the main thing is that a neutron can fall apart into a proton and electron. So if you've got a nucleus with too many neutrons, it has the possibility of changing into a nucleus that has an additional proton and kick out an electron. It will evolve from one element to another. It'll work its way toward the bottom of the periodic chart. So is this true? Uranium-239 is unstable. Got too many neutrons. It turns into the next element in the periodic chart, Neptunium, which of course you've heard about, and it's everywhere, right? No. That's got 93 protons. Where'd the extra proton come from? It used to be a neutron, but it fell apart because there were too many. It turns out Neptunium-239 is also unstable. It still has too many neutrons for its taste, so one of them falls apart and kicks into a proton and an electron that it throws away, and an antineutrino, sorry. And it becomes an element you have heard of, plutonium-239. So bottom line, too many neutrons, you end up tossing, they tend to break and they throw out an electron and become a heavier element. It's a process known as beta decay, but that's just naming things. Bottom line is that too many protons is a bad thing, too many neutrons is a bad thing. It's a delicate balance. And so some of the large nuclei fall apart spontaneously. And so uranium exists in nature, which makes it, okay, so it's considered one of the naturally occurring elements, but all of the uranium atoms are unstable. They all fall apart gradually. There are two what are called isotopes of uranium. An isotope is a nucleus that has, well, we're comparing two isotopes. Two nuclei that have the same number of protons. So both of the isotopes of uranium have the same number of, did I say that right? They have the same number of protons. They both have 92. That makes them uranium because they attract 92 electrons. They have the chemistry of uranium. But they differ in how many neutrons they have. One has 143 and one of them has 146. There are other uraniums you can create, but they don't live very long. I told you, if you make uranium-239, it doesn't live very long. It becomes Neptunium, which then becomes plutonium. So these two different nuclei, one with 3 more neutrons than the other, are chemically indistinguishable. They are isotopes of each other. But they have slightly different masses. And they have different lifetimes against radioactive decay. Radioactive decay is a statistical process, and it's characterized by half-life. So that if you have a whole box full of uranium-235 nuclei, and you watch them for a long period of time, you'll lose about half of the uranium-235s in just under 1 billion years. So that's called a half-life, means that how long do you have to wait before half the nuclei statistically are exploded. Uranium-238 has a longer half-life of something like 4 billion years. So if you start with a mixture, a 50-50 mixture of 235 and 238, you okay with me using those terms, 235, 238? They're both uranium, but they're different in the number of neutrons. Questions? So if you have them sitting there 50-50 to start with, you wait, you're going to lose the 235 faster than you lose the 238. And you'll eventually end up with mostly 238 because it lives longer on average. And that's the situation here on Earth, is we started with probably some relatively even mix way back when Earth was formed of the two nuclei. They were created in some huge explosion in the stars. Exactly which, potentially a single star exploding, potentially neutron stars crashing into each other. In any case, we ended up with these things. The Earth was built out of those remnants of stellar catastrophes or cosmic catastrophes, and the 235 has been vanishing faster than the 238 over the past 4 or 5 billion years that the Earth's been around waiting. And so uranium-235 is pretty rare, which is a good thing. Why? Because uranium-235 is the wherewithal to make a nuclear weapon. If you just wait for stuff to explode, before I go completely past this, there are lots of things that have there are things that have radioactive decay going on in them. For example, this is an old watch that has a phosphorescent hand, so you can read it in the dark, and they have radium in them, which is a radioactive element. What you're hearing here is those little tiny, the nuclei in radium falling apart. They've been waiting here for zillions of years, and right now, right today, they're falling apart, and you're hearing the ping, ping, pings of them falling apart. Is that okay? Smoke detector. Smoke detectors are one of the rare cases where they'll let you actually have a radioactive material in your house. It's americium, which falls apart, I believe, by beta decay, and it kicks out an electron. And that's used to put charge on dust. So you can, or smoke, so you can find the smoke particles. The mantles for camping lanterns they work best if they've got thorium in them. And thorium is a radioactive element. So they allow, last I knew, they still allowed the sale of thorium-containing stove mantles. They glow beautifully white when you heat them. This is, I think it's Vistaware, is that what it's called? It's a glazed ceramic that was available 50, 70 years ago, no longer available. That beautiful orange color, it's got uranium in it. So you go to the pottery place and you paint your potteries. They don't give you uranium-based glazes anymore, but this is uranium-based glaze. It's a collector's item these days. Okay? I guess that's the whole story. That's good enough. All right? So, yeah, Jesse? Why doesn't the object itself fall apart? Because it's the atoms in that glaze, for example, they're falling apart. They're probably, what are they becoming? God, I'm not sure what the decay process would take them to. They're probably working their way down towards lead, step by step. But it's happening in that atom in the midst of 100 billion other atoms that won't explode in our lifetime. So yeah, you're losing one atom in this vast collection. It just doesn't have enough effect to really cause trouble. If you have more seriously radioactive stuff, which exists, you can have the whole thing fall apart badly. And this is one of the concerns with trying to encapsulate and store radioactive junk from reactors, from nuclear weapons programs and stuff. How do you store it in something that holds together for long enough for the radioactive decay to really sort of finish? And these are poorly solved problems. They're potential trouble. Because yeah, you make this beautiful, you turn it all into ceramic like that. Ooh, it's done. Nothing will ever change. Well, it's actually undergoing damage. Okay, it's falling apart. So that's simple radioactive decay. It turns out that you can take some of these nuclei, not all, but a certain collection of these radioactive nuclei. Radioactive nuclei are common. There's an isotope of potassium, naturally occurring isotope of potassium that is radioactive. So we are all somewhat radioactive ourselves. I heard somebody talking about measuring radioactivity in terms of the number of bananas, which I thought was really nice. Like, that's 1,000 bananas worth of radioactivity. Because bananas are radioactive, just not very much. Because they got potassium in them, right? It's an essential nutrient. It's part of our bodies. We are not perfectly free of radiation and radioactivity. Anyway, the radioactivity is the natural falling apart of nuclei that are not quite stable. They're almost stable. Classically, they would be stable. Quantum mechanically, they're not. They tunnel through and fall apart. There are many nuclei that are truly stable. They will never fall apart. Life of the universe forever. Okay? There are some nuclei that if you hit them with projectiles, they will fall apart spontaneous. You can cause them, you can induce them to fall apart. And furthermore, there are ones where you can induce them to fall apart into multiple big fragments. And uranium-235 is an example of that. It is fissionable. So to perk along here, if you take uranium-235 and hit it with a projectile, you can crack it. And when you crack it, it releases way more energy than was involved in inducing the crack. You basically split the Velcro, boom, the whole thing flies apart. And that is not true of uranium-238. When you throw a neutron, it's not fissionable. I should say the projectile of choice, the obvious projectile to crack an unstable nucleus like uranium-235 is a neutron. Why a neutron? Well, a proton won't work because the nucleus, uranium-235, will know the proton's coming. They repel each other ferociously. They're both positively charged. Bad choice. How about an electron? Well, you can use an electron. It's going to be attracted, but it's so dinky. It's like trying to break a car by throwing a fly at it. It doesn't happen, right? You hit plenty of flies driving down the road, no consequences. So if you want to break a uranium-235 nucleus, you want to hit it with something that's electrically neutral and hit it hard. Neutron's the obvious choice. And so neutrons can break uranium-235, a process known as induced fission. And the pieces that come flying off include neutrons. So that's an interesting situation. You can throw an initial neutron in, break a uranium-235, have neutrons come flying out along with a lot of other particles, and use those neutrons to break other uranium-235 nuclei, a process known as a chain reaction. So I'm going to zap, there we go. So a chain reaction is where one neutron comes in, breaks a uranium-235 nucleus or something similarly fissionable. An example of another fissionable nucleus is plutonium-239. So you can crack the uranium-235, it flies apart, it cracks other uranium-235s by way of the neutrons that are freed up, which break other uranium-235s, and it gets carried away. And this is a chain reaction, and the question is basically, is the chain reaction efficient enough that it gets bigger and bigger? With each sort of generation of destruction, do you get more and more destruction in the next generation by way of the projectiles released by the first generation? Or does it sort of peter out? And that's where the concept of a critical mass comes in. If you've got enough material and it's strategically located so that this process of chain reaction gets stronger and stronger with each generation, you eventually end up with a disaster. There's a huge number of nuclei shattered, each one releasing a lot of electrostatic potential energy. And you got to meet certain criteria. You got to have enough material, you got to have it packed tightly enough, it's got to be fissionable, of course, and you have to start with a neutron to get the whole thing going. And when you do that, you get an explosion. In nuclear power, they do this, but they keep it under control. They make sure that the generations don't get carried away. This generation produces neutrons and stuff, which cause the next generation, which creates neutrons, which cause the next generation, but you don't make the generations get bigger and bigger and bigger and bigger. And there are techniques for controlling that. In a weapon, you want the generations to get bigger at a furious pace. So the first generation, you break 1 nucleus. Second generation, you break 2. Third generation, you break 4. Fourth generation, you break 8. It just goes, blows up exponentially. And these are the fission bombs of World War II. Were based on this concept. The one that was tested at Alamogordo and subsequently used to kill a whole lot of people in Nagasaki. And if you ever have the opportunity to visit the Hiroshima, it's a moving experience. I mean, it's just, I'm glad personally that I wasn't around during that era because I could see, easily the Manhattan Project easily gotten swept up in the enthusiasm and excitement of that. But these are horrible things. So the first test explosion and the one used in Nagasaki involved plutonium. They synthesized plutonium in a heroic effort, but they managed to they made the plutonium. They made enough plutonium that by itself, it was a sphere, it was not a critical mass, which means not that they didn't have enough material, it's that it was too diffuse to maintain a chain reaction that got bigger and bigger. The nuclei were spaced apart by the chemistry of plutonium, which put them too far apart for this little object to sustain a chain reaction that got bigger and bigger. To make the chain reaction that got bigger and bigger, they crushed the sphere with explosives. And it turns out it's possible to take material and crush it to huge density briefly. It'll bounce, but you can actually temporarily get it very tightly packed. And during that tight packing, the chain reaction happened, the whole thing exploded. And that was that. The Hiroshima bomb was uranium-235. And There were technical reasons why they used a different technique with 235. They simply made a sphere of uranium-235 that had a hollow core. It had a cylinder missing. And once the cylinder was introduced with a cannon, it was shot into the middle of that sphere, the chain reaction came and it exploded. To illustrate chain reaction, having talked about the sad reality of the actual weapons, this is a chain reaction involving mousetraps. Each mousetrap has 2 neutrons, bouncy balls, sitting in it, waiting there. Classically, they're stable forever. Quantum mechanically, in principle, there could come a moment when one of them snaps spontaneously. But we're going to induce the snapping with an initial neutron. I'd have one of you guys come do it, but we're short on time, so I'm going to introduce the initial neutron. And ready? Get set. Chain reaction.